All right, so it's my pleasure to introduce you today to Mong-Han Huang. So Mong-Han did his undergrad and master's degree in Taiwan at the National University of Taiwan in physics and geology. After that, he went to California to get his PhD from University of California at Berkeley in 2014. After that, he got his postdoc from the Jet Propulsion Laboratory in California. And recently, last year, he started his position at the University of Maryland, where he's now an assistant professor. So today he will talk about how we can use space geodesy to image crustal deformation.
Oh, I have my mic. Can you guys hear me okay? So today is my great pleasure to be here and present part of my work to you guys. So in general, I use space geodesy. That means I use satellite data or data that came from the satellite that monitor the surface deformation on Earth, and then how we use those kind of information to understand either the natural hazard, something like earthquake potential or landslides, or even just to understand the upper crustal or the lithosphere scale internal properties. So here I'm just going to present two examples of what I've been doing. So to begin with, I just want to have everybody on the same page. So I will be talking about what is actually earthquakes and earthquake cycles, and how we use this kind of satellite data to monitor that. So now imagine that you build a fence here on top of a fault. It's not a good idea, but a lot of people just don't know there was a fault, and you probably know why in a minute. So imagine there's a fence built on top of a fault, and in fact, on two sides of a fault, they belong to different tectonic plates. So now we can imagine you can say this is a this is a Pacific plate, and then this is a North American plate. So we know it's moving. So in the period of time when the plate pass each other, they are going to introduce some internal deformation. So within a period of time, let's say 100 years, you put a fence there, and then you will start to see there's a, oops, not very good at this. So you will see there's a bending of a fence, and then that bending is due to the plate motion. So you see that this plate is moving toward northwest, whereas this plate is moving towards southeast. And you just see creeping going on, and there's no earthquake you can feel. And the reason is because there are some internal frictional strength within the fault. So that strength was not high enough to break the fault. So we call it the fault was locked. And during that period of time, you see those kind of internal deformation, but you don't feel the earthquake. And we call it interseismic period. So this might be going on for years to 100 years, or maybe even 1,000 years. And then one day this will happen. So that is when that energy that's stored in the fault that was high, it was so great that the fault strength can no longer hold it, then the fault will break. So when that break, there will be a lot of motions here. So here you can see the fence was broken at this time. And then if there's a cow or a person there, you will feel a lot of ground motion. So you guys are, I guess most of you guys are from East Coast, so you probably only feel like Virginia earthquake in 2010. But where I did my PhD at UC Berkeley, I feel maybe 10 earthquakes 10 earthquakes in my whole PhD, like 5-year PhD time. But before I was in California, I'm from Taiwan, I probably feel 10 per year. And in fact, my master's student went with me to Taiwan during the summer. I told her you might feel an earthquake, and we feel one like the first night we were there. Anyway, so that is so the kind of ground motion we will feel. And after that, it's not the end of a story, because there will be some adjustment. There was a lot of motion, so it will be chaotic. So there will be a period of time for that chaotic to cool down, and then we call it a post-seismic time period. And after that, in the meanwhile, the plate is still loading all the time. So soon after this post-seismic time period, and then you will go back to the interseismic period and then cycle through the time. So that is what we are seeing nowadays. So what it actually looks like is like this. So if now we go to California and then we focus on the San Francisco Bay Area. So here you are seeing a map of, we call it a GPS record. So this is the same GPS as your handheld GPS, but they are more precise. The precision of that is probably less than a few millimeters. So everything that's moving a few millimeters per year will be recorded by those kind of device. So each arrow represents one GPS station. So now if we set this triangle as a reference station, so everything is moving relative to this triangle here, then the GPS stations west of this triangle is moving toward northwest. East of this triangle is moving toward southeast. So that will look pretty much like this, right? You have this, if there was a gigantic fence built here 100 years ago, then you will probably see the fence bending like this. It will look like that. And in fact, all the black curves here represent active faults in California, in the Bay Area. So that is what happens during the interseismic time period. So in the cold seismic time period, that is when there's a snap. So when the fault breaks. So this is another example of an actual earthquake that happened in 2010. That was in the Baja, California, roughly here. So this map shows located this red square. This red line here is the fault. There's a fault surface rupture, so that will be this fault line. So all the arrows, again, those are GPS stations. So you can see the GPS stations that are close to the fault has a lot of movement. GPS stations away from the fault, they have much lower amount of displacement. And we call this kind of displacement co-seismic displacement. So that also looks like this kind of scenario. If you have the fence here, you can see a lot of motion near the fault, and then it will be a smaller and smaller motion when you are far away from the fault. So if you keep recording those positions from GPS continuously after your earthquake, you will see that actually the crust is still moving after your earthquake. So this is a collection of data between 2010 to 2015. So it's a 5 years record. Then you see there's roughly a 5 centimeters of displacement after even after your earthquake. So earlier on, this is a co-seismic. You can see this arrow, and this is a scale. This is more than 1 meter of displacement close to the fault. But 5 years later, you still have roughly 5 centimeters of displacement. So that is roughly 10% of the co-seismic displacement. So those are things we can record on the surface. And then all the GPS that communicate with a GPS satellite. So it's how you get the position throughout the time. So in order to understand what the fault is moving, we really need to rely on surface record. So for example, this is a 3D plot, and then you have those arrows that represent different GPS stations. Then based on the GPS station, the motion of a GPS station, you might be able to image what's actually happening along the fault system. So in this example, those surface displacement can be explained by the creeping along the fault that is really deep. So very deep means that's below the brittle ductile transition that is roughly 15-kilometer depth. So below that depth, the temperature is much greater, that the fault property becomes very weak, so they cannot hold any energy. So any kind of motion will start to drive the fault to slip past each other. And for those kind of motion, that doesn't generate seismicity. So how well you can image that depending on how good the network you have on the surface. On the other hand, when there's a co-seismic or an earthquake event, you have those GPS data as well, and you see more displacement close to the fault. So here you can imagine that those movement very close to the fault might be due to something that happens shallower. So those are shallower slip along the fault. So again, in order to get better image of that, you need more observations. So how many observations is sufficient? And then also, we'll say yes, everywhere. But to put one GPS station here, they may cost, say, $30,000. Can we put just $1 billion everywhere and get a GPS everywhere on Earth? Probably not realistic. You'll probably not get this kind of funding from NSF if you just propose that. So we need to find a new solution that we can actually image the entire crustal system without spending too much money. So that comes to a new idea that we actually just use radar data from the satellite that's orbiting the Earth. So this is an idea, and then the kind of technology we call InSAR. So the full name is interferometric synthetic aperture radar. So synthetic aperture radar, or SAR, it is a kind of radar image. And they come from the sensor mounted on the spacecraft, and then the satellite or a spacecraft orbiting the Earth, and then they return to the same location, say every month or every week or every year. So whenever it passed by the same area, it will send the radar signal to the surface and then get a return signal. And because it comes back all the time, so when there's a surface displacement happened, and then you have an image before the event and an image after the event, then you will be able to use something called the interferometry of the phase of this SAR data. Then you will be able to actually see what is happening on the Earth or the surface. So this is an example of what we call co-seismic displacement due to this 2014 magnitude 6.2 Napa earthquake that happened in the North Bay. So here, this red curve shows you the surface rupture by the earthquake, and the star shows the epicenter. All the fringes you are seeing represent the amount of surface that is moving during the earthquake. It might look very overwhelming, but if you know how to read a contour line to know the topography, this is pretty much the same principle. So when you read a topographic map, if there's a contour line, you know that when the lines are very close to each other, that means you have high relief. So maybe you are going to see a mountain or a huge basin. So as long as you know the contour interval, then you know the surface elevation by looking at a contour map. So this is exactly the same principle, but now instead of looking at the surface topography, you are looking at the surface deformation. So now I tell you that the fringe interval or the contour interval here is 2.8 centimeter. So when you count 10 fringes here, then you know, oh, from here to here, there has been 28 centimeter of surface displacement. So that is how you read it. Okay, so now I'm going to show you the first study case that is in my hometown in Taiwan. So the title is a total variation regularization of geodetically constrained block models in southwestern Taiwan. So this is a geologic map of Taiwan. So in case we don't know where it is located between the collision zone of the Eurasian plate on the west and the Philippine Sea plate on the east. So in this geologic map, this line here roughly shows the plate boundary. And then the different color represent different geologic units in Taiwan. In general, from west to east, you have a higher and higher grade of metamorphism. So on the west part of Taiwan, those are sedimentary rocks. But close to the plate boundary, it goes from low grade to high grade metamorphic rocks. If you look at those GPS measurements, then you can see how active the crustal deformation is in Taiwan during the interseismic interval. So each arrow here, again, is one GPS station. So this is the motion relative to this station here, where I say is a reference point. You also see a lot of circles, and the color of the circle, that represents the vertical displacement of the GPS. So we see not only horizontal, but also vertical displacement. So currently, the Philippine sea plate is colliding roughly 7 centimeters toward this reference station. So it's quite a lot of displacement. It's roughly 2 to 3 times faster than in California. And California is already the most active plate margin in the United States. And the color here is a vertical, and then you see there are some dark blue to red color. The blue color means surface subsidence, so those are due to groundwater pumping. So a lot of pumping to get groundwater, and then you can induce land subsidence. And those uplifts are probably associated with tectonic uplifting. So Taiwan is very, very active. And then here I just want to show you an example in southwest Taiwan. So in 2004, there was a new tunnel built as part of a highway system. What they didn't know is they built this tunnel through an active fault zone. So in 2004, there was a couple years after this was done, and before the highway was open, they started to notice there are cracks on the wall. So here, and then there's also cracks on the road. So some years later, in 2012, I just found an image from Google Street View. So you can see there's a ramp. So and then there are some modifications. So this section is exactly here. At that time, this is a straight line, and everything is straight. But here you can see there's a ramp. So there was already like a 30 centimeter of uplift just inside that tunnel. So this is 4 years ago. I went back to Taiwan and I took this photo, and then you can see there's the ceiling here, the light. There's a step. And remember, just 10 years ago, everything was flat here, and then now you can see this road. The line here is no longer a straight line. So that was already 1 meter of uplift since 2004. So that is telling you how active the Earth could be. So you may be able to see something like that even just in a decade, and you can see 1 meter of displacement. So that is how active Taiwan is. Okay, so that is what we see actually from the structure. If we see it from the space, then this is what we are seeing. So the satellite flies by Taiwan in 2 kinds of orbit. The first one, we call it descending. That means it's flying from north to south. It's looking toward west. So here the color, the blue color represents either its surface subsidence or westward movement. And red means either uplift or eastward movement. And this is an ascending track, so it's seeing from west to east. So the color will be, the horizontal motion will be the opposite. So here, blue means either subsidence or eastward motion. Red means either uplift or westward motion. So in those ascending and descending track of interferogram, if you see there's a red color, if both show you red, that means it's probably uplift. If one is red and one is blue, that means it's probably a lot of horizontal motion. So that's the difference between ascending and descending. So by combining both ascending, descending, and then using GPS data to help, and we were able to actually estimate the 3 components. So we were able to get horizontal and vertical of crustal deformation in southwest Taiwan. So this is an example. The background pixels are the InSAR measurements, and the circles are GPS. So the color represents east-west motion or north-south or vertical. So let's look at vertical first. You can see all the blue color means the surface subsidence. So those are, unfortunately, all associated with human-induced subsidence due to groundwater pumping. And then by here, you can see some red color. And then the black lines here represent active fault zones in Taiwan. So you can see they are very close to those active faults, so you can interpret those are associated with the fault movement during the interseismic period. Let's look at east-west component. You can see there's a gradual change of color from red to blue. That means in this part, the surface is moving toward east relative to the reference station. And south of the reference station is moving toward west. So there's a lot of horizontal motion in Taiwan as well. So now comes to the question I asked myself in the very beginning, that how many data do we need to explain a fault movement during the interseismic? So now we have overwhelming amount of data we have, then we are happy. So now we can start working on the next phase. How do we model it? Because we don't know, maybe there are way more faults than we know about, because everything is covered by sediments and buildings, and there might be faults underneath that we didn't know about. So what I was trying to do is just to collect all the data we have. So we have all the faults, either published by the Central Geologic Survey in Taiwan, or just compile all the old geologic map compiled by the oil companies. So I try to map all the faults that I can think of and then find, and then I can come up with sort of a fault model, and then see if this fault model is able to explain the InSAR observation I'm seeing. So it kind of comes into another problem that every data you have, there's something called uncertainty. So probably not everything you are seeing from your data is correct. So if you just throw in all the faults trying to explain everything, you might be able to explain all of your data. But what you don't know is actually whether or not you are explaining your noise or explaining your actual data. So after talking with my second author or my collaborator, we found out there's a more smart way to approach this. So now if I go back to this slide. Now if I allow, so every fault can define a block. So there are a lot of blocks in Taiwan, and one block is, for example, this block is separated by 4 faults. So what we're trying to do is we're allowing all the blocks to rotate or move or pass each other around in order to explain our geodetic data. So this is an example of a block model. So here there are 3 blocks, so block 1, 2, and 3. So now if we assume block 3 is fixed, it's not moving, and then block 1 and 2 can move. So actually the fault movement along this fault will be the difference between the motion between block number 1 and block number 2. And there's another fault movement here, and that will be the difference between movement between block 1, 2, and 3. So you have different kind of fault movement due to this. The problem we have now is whether or not block 1 and block 2 are the same block, and then this fault doesn't exist, or actually this fault exists, and then we need both blocks to be moving. So if that is the case, then block 1 and 2 will share the same rotation pole. So they are rotating about the same location, and then you can imagine then this fault, there will be 0 motion on the fault because both 1 and 2 are moving together. So whether this is the case or that is the case will depending on how much you can explain your data given by the data uncertainty. So the method we come up with is we call it a total variance regularization. So that is to minimize the difference between your model and your data with a sufficient amount of smoothing using L1 norm regularization. So I'm not going to go through the detail about this approach, but in principle, we are trying to allow every block to move so we can potentially fit the data very, very well because you have more parameter to fit data, so you will get the lowest misfit. And then we start to group some of the blocks. Then you are start to lose your model parameters. So you may not be able to fit the data as well as you were. but maybe that is more reasonable because the misfit you are having now is actually the data noise. So we can do this approach from allowing everything to move to nothing can move. Then we will have something like this. So the blue curve here shows you the grouping. So on the left-hand side, we allow all the blocks to move. All the way to the right-hand side, you can see there's only 3 blocks. And then the red curve here shows you the misfit. So when you allow everything to move, you have the lowest misfit. So here's 4 millimeter per year of misfit. Up to when you don't allow anything to move, then you have 16 millimeter per year of misfit. Then we can say, so this is the scenario when you allow everything to move. So you have all the faults moving. So color here represent the slip along the fault. To nothing is moving, so you basically group everything here, and you have huge amount of misfit. So how we determine this is the ideal grouping will be when the misfit we have is roughly the same as the uncertainty of the data that we can estimate. Then that will be at here. So here we have, say, 22 blocks, and then it's able to explain most of the data, and then we have roughly almost 4 millimeter of misfit.
Excuse me, can I ask?
Yeah.
To what extent are you assuming that these are all strike slip, or are you putting a 3-dimensional?
Yeah, it's a.
The complexity of these blocks can be pretty extreme.
Right, it's a very great question. So in this kind of practice, we only use a horizontal motion. So we do not consider vertical motion. And whether or not the fault is dry slip or a dip slip is really depending on the orientation of the fault relative to the block motion. So everything, the convergent rate or strike slip rate is a result of the difference between the 2 blocks.
Can I follow up on that?
Yeah.
As far as I remember from geological maps, you estimate
Yeah, I will actually get into that later. So again, now just assume we are not taking vertical into account at all. All of this we are trying to explain is a horizontal motion. So this is the preferred model we have. So black lines means those are faults, but we assume they are grouped. So there's no relative motion along the fault. And then you can see there are major fault movement along here and then along here. If you compare with the InSAR data in horizontal, then you can see it's trying to explain all of those eastward motion and all of that westward motion. So that is the result. However, if you look at the vertical, so again, we did not use vertical in our model. Then you can see actually the majority of the uplift comes from here. And there isn't too much going on here, even though you have a lot of horizontal motion here or here, but you don't really see vertical. So, and this the misfit. So we can see some misfits here. That may be because of the block geometry we came up with is not good enough to explain the data. And then if we look at the velocity gradient, so this is the displacement, and then you take a first derivative in space, then you get a gradient. So it's supposed to highlight the deformation. So white means there's a lower amount of deformation, and then red means there's more surface deformation. This is a horizontal, and this is a vertical. So if you compare the horizontal with the preferred model, then you can see most of the red color correlates with where you see the red color here. So that means you are explaining those surface gradient, velocity gradient. But if you look at vertical, it's not in a very good agreement. Well, in the northern part, it's easy to explain because of this gradient is due to surface subsidence, due to groundwater pumping. So there's nothing, has nothing to do with tectonics. So of course, you are not going to explain that. But in this part, you have a lot of horizontal motion, but you don't see it in vertical. Then we came up with this hypothesis that maybe because of most of the faults, the thrust. I don't think I have a slide here, but there, in a thrust fault system, you have a flat and ramp. So the ramp will be when the fault is getting close to the surface, and the flat is in the deeper part. The fault becomes more horizontal, and then we call that horizontal fault segment. We call it detachment. So we believe that those motions are due to the detachment slip. So because the detachment is sub-horizontal, so it produces mostly horizontal motion instead of vertical motion. And what you can predict to vertical motion will be from those ramps. So those ramps give you lower amount of horizontal motion, but more vertical motion. So that is probably a separation between horizontal and vertical. And then that will imply that in the interseismic period in southwest Taiwan, the detachment is creeping, but the ramp is locked, just like the famous cartoon I showed you earlier, that it was just locked. It's just some internal creeping, but there's just internal deformation, but there's no creep along the fault. In this case, it's different from a strike slip fault system because it's now deep slip, so you see something going on in vertical. Yeah, I can get back into that later, and then I have a cross section, but this is not in here right now. All right, so to summarize this part, I just want to say that the space geodesy is able to reveal interseismic crustal deformation in southwest Taiwan. And then we are able to build a block models based on geologic map. And then based on this total variation regularization algorithm, we are suggesting that most of the fault ramps within the western foothills are locked. So those ramps are locked. But there's a creeping along the detachment. So this approach shows an efficient and objective way to estimate the fault activity in an active fault zone in the interseismic area, and it can be applied to something like Taiwan. It can also be applied to somewhere like California. Any question for this part? Yes, Tim. Yes, but we like to rely on sort of like a traditional like fault mapping because there's surface evidence that we actually see, we actually can have geologic constraint on that. So we like to start with more like a actual geologic mapping than just take the data and then say, oh, there must be a fault. Yes. Yeah, that's an interesting point. In somewhere like Taiwan, you have earthquake all the time. So for interseismic, that means something that doesn't change in time. But in Taiwan, the reality is there are always some earthquakes happening. So that those earthquakes will influence the interseismic estimate. So my comment will be, if you have a very long observation time period, then for sure you can separate different time period and see how faults slip in time. But overall, we are trying to remove those earthquake contribution and get a pure sort of no earthquake involved interseismic period. That is a goal. Okay, so I'm gonna move on to a second topic. It's totally different, but it's also using InSAR dataset. So the title is the seasonal slow-moving landslides and hazard in ISO, India, revealed from InSAR. So this is the picture of the town ISO, and then we'll get back into this. So I want to begin with showing you the global landslide catalog. So here, all the circles represent a recorded landslide that happened between, I think between 2007 and 2016. the color of the circle represents how many fatalities. So you see there are a lot of records in the US, but there's really low fatalities. In Eastern Asia, there are a lot of landslides and also a lot of fatalities, especially it's tectonically active and there's a lot of monsoon, so it's induced a lot of rainfall-induced landslides. I want to focus on India. So this is the map of India, and then this is the eastern part of India, so it's actually past Bangladesh. So this area is between Bangladesh and Myanmar. So if you look at this map here, you can see there's sort of like a light colored dot here. That is a town Aizawl. That's the capital of the province, Mizoram. If I show you a cross section of this region, then you can see this is actually part of a subduction zone. And you can see here, this is an Indian plate subducting underneath the Burma plate. All the circles here represent an earthquake event and its focal mechanism. So you can see it's seismically active. This is a simplified fault structure here. So in this part, this is sort of a accretional wedge, and then it can host a lot of earthquakes. Unfortunately, the town Aizawl is located here. So this is an area where an earthquake won't surprise you. Okay, so there's a closer look of the town. All the white color here represent buildings. So this is a town built on top of a mountain, and just cut down the tree and then put buildings. This is a photo actually people took when they were there. So it's sort of a typical image of this region where you have dense amount of buildings building on top of steep hill slopes. So this is sort of a promotion for natural hazard because there are a lot of precipitation, there are a lot of people, and there are a lot of buildings. But the biggest problem is, first, the town is huge. There are more than 200,000 population here. There's currently no dense instrumentation measurements. So people actually first don't really know what is the tectonic movement here. Second, do not know which part of a town is subject to slow-moving landslide, which part of a town is more rigid. So and then it has been having some serious amount of landslide problems. So initially, I didn't know anything about this town. But a few years ago, two Berkeley undergraduate students, they got a summer internship and then went to this town. And so that was by Carly Sheffer and Aurora Smelty. So they went they went there and then map all and go around the town trying to map any kind of evidence that shows slow-moving landslide. So this is what they did. They walk around trying to interview people. Some people would tell them that, yes, please come to my house because this part of the ground was here 10 years ago. And then a few years ago, there was a rainfall. A month later, this piece of the land just disappeared. So now part of my house has no foundation. Sometimes they will see something like that. So this is a ground surface, and then they see some cracks. And they can also measure some motion along the cracks that indicate this is a slow-moving landslide. So they spend an entire month walk around the town trying to record and document this and take GPS location. So they actually found there are two clusters. So this is a town, and then they found one cluster here. They call it a Renther Sports Complex on the east. And in the south, they see a Renther Van Sinking area. So they just how they named the two areas. So they came back and came to me and showed me this data and asked for some suggestions. I say, since I'm doing satellite imagery and remote sensing, maybe I can use SAR and then InSAR and see what can I see. So we took this data called ELOS-1. So this is a satellite that flies by the same region every 45 days. So because it only flies by every 45 days, so the resolution or the image quality is not great. Even that, we were able to kind of see something. So here you can see those circles that represent a point that InSAR can see. Yellow means they are stable, red means they are unstable. So you can sort of see red color here represents something unstable, and that is actually where they map a cluster of SlowMoving landslides. On the other hand, in the south, you really don't see anything from InSAR, where they map a lot of SlowMoving landslides. So that is what we got in 2014 when I was still a graduate student. When I was a postdoc, I mentioned this to my Italian colleague, and then he was able to get the Italian Cosmos SkyMat satellite. So it's a 4-satellite constellation. So they fly by the same area every 2 to 6 days. So you have a lot denser repeating cycle. And you will actually be able to see something. So in this region where we can see a much detailed outline of the landslide motion, and also in the south, we are able to map this area. So if I go back and then put things together, you can see the white circles are the in situ measurements, and then the red pixels are the InSAR. So it agrees fairly well, and then agrees fairly well here as well. In fact, if I look into the entire town, we can just see very clearly this part is moving and this part is moving. And actually, it moved toward here and goes downward here. So there's another split here. They didn't go there, so they did not know. And also, there's another one here, and the same. They didn't go there, so they didn't know. So that shows you how powerful this technology could be. You don't need to go there and survey everywhere. You can just look at this image and know what you are expecting, and then go there and check the surface evidence. It's not only to show you a map. If you take every pixel, actually you can see the time history of the motion. So here is an example of a pixel in this area, and you can see this is time, and vertical is the displacement. So you can see the motion is actually not a straight line. It goes slower during the dry season, and then faster during the wet season. So the wet season is summer, dry season in the winter in this part. It's sort of similar, but not very clear in the south. If I remove the trend, then you actually see a little bit clear that it moves faster in the summer and slow down in the winter. So now if I separate out dry and wet season, you can also see that in the dry season, the motion is, the color is closer to yellow, so that is roughly 2 centimeters per year. In the wet season, it is roughly 5 centimeters per year velocity. And then if you compare dry and wet, you can see wet season is roughly 6 times faster than the dry season. If you look at the sliding rate, you can see the variation between 0 and 0.3. So it looks seasonal, and then we want to understand why it is seasonal. So one other thing that is probably seasonal is actually precipitation. So this implies that the velocity of this landslide is driven by precipitation of the area. So we took the satellite-based stream precipitation model of the same area. We see, in fact, they correlate fairly well if you just look at the plots. So that is all good, and then we see there's sort of a delay between the peak landslide motion and the peak of the precipitation. So that gives us a hint that if we can understand this process very well, maybe in the future we are able to send out a warning if there's a precipitation rate higher than the threshold, then we can warn a town and evacuate people. So that's sort of a long-term goal for this work. So for a short term, we are trying to just explain why there's a lag. So we use this model that we assume there's precipitation on the surface, and then the water will infiltrate downward. So when the infiltration hit sort of a sliding surface, it will increase the pore-free pressure, and then that will drive the velocity to move faster. So this can be explained by using a 1D diffusion equation. So it's a really simple 1D diffusion equation. P here is a pore-free pressure, T is time, Z is the depth, and then D is the hydraulic diffusivity. And then the boundary condition will be that the surface will, the pressure on the surface will be purely driven by the precipitation. So here R of T is a precipitation rate in time. Luckily, there's an easy analytical solution of this equation. So this is just a solution of that form. So this is a pressure at depth at different time. And then all of the parameter with the red underline, those are the parameter of the unknowns. So we know the rest of them, and then we don't know D and Z. So we can just vary D and Z and then see the prediction of this P, and then compare with our actual InSAR observation, and then we can determine what kind of depth and then the diffusivity we want. Unfortunately, the fitting looks like this. So here, blue color means you have good fitting, red means you don't fit well. So it looks like there's a curvature here that you can fit things fairly well. So there's a trade-off when you have low diffusivity, then you have shallow sliding depth. When you have high diffusivity, then you have a deeper sliding depth. So we use empirical measurements to constrain this depth. So by this Henweger et al. Paper, they document landslides in the world, and they found there's a relationship between the landslide depth and the landslide area. So you can see there's a correlation between area and then depth. Because we know the area of this landslide, so we can just take the area and then we can estimate the depth. So by doing that, we can fix the depth here, and then we will know the diffusivity is roughly 10 to the -4 meters squared per second. By applying that parameter, then we can start to predict the landslide behavior. So taking this precipitation as our input, the red curve here will be our model porphyry pressure, and then that is a scenario where we can fit the observation the best. So if I only take the year 2012 and 2013, so that would be this time period, it seems like everything is fitting fairly well. And in fact, if you plot a normalized sliding rate versus the normalized porphyry pressure, you can see this is sort of a one-by-one curve. However, if I move forward in time, in 2014 and 15, you start to see there's a deviation. So it looks like the landslide sliding rate is not very sensitive to porphyry pressure anymore. Not like before, it was one by one, so you have this amount of porphyry pressure increase, you have this amount of landslides. By slowing down, become insensitive. I was very confused, and then I went to the undergrads who went there and asked them. I told them about this, and then they told me, "Oh, there's one thing I forgot to tell you. The Indian government saw this problem, so they built a lot of dams in 2014. So this is a photo of that, because they are trying to slow down the landslide speed. So in fact, what they are doing actually has some positive feedback. So now the response of porphyry pressure is not as sensitive as before, and it has been slowing down. So the summary of this part is our InSAR shows a very good agreement with the surface with the field observation, and then we indeed see a seasonal SlowMoving landslides. In dry year is in this range. In the wet year is roughly 3 to 12 centimeters per year, and then the velocity is generally 20 days after the peak precipitation. And then the change of porphyry pressure at depth can explain the seasonal velocity variation during 2012 and 14. And then the construction of this retaining wall might have slowed down and changed the behavior of a landslide. Okay, so that's pretty much what I want to talk about today. And I just, in the very last slide, I just want to tell you that all of the application and satellite data I've been showing are either from European Space Agency. But in a few years, NASA is actually going to launch our very first space satellite that carries a SAR sensor. It's called InSAR. And then it's supposed to be fly by the Earth every 12 days. So I hope we will learn some more stuff from this new satellite. Thank you.
Questions for Mong-Han?
Yeah, so if I go back a few slides. So indeed, there are some cluster of this. I do not know exactly the reason, because if you look at the drainage basin, there should be another one here, but that one is pretty stable. All I can think about is actually man-made, because there's some toe cutting here. So they have been modifying the road, and there's another road here, so they've been cutting the toe. So they are making the whole landslide area be more unstable. So they are doing that here and also here. So that might be a cause of that. Yeah, so before they cut the toe, so now they are building retaining wall. But we don't know that if building the retaining wall is the ultimate solution, or maybe if there's another accumulation of even higher or greater porphyry pressure, maybe it will induce an even greater event. So it'll be less frequent, but when that happens, it will be much bigger scale. So we don't know that yet.
Any other question, Tim?
Mm-hmm. Oh, you mean it's more in phase? We don't know. It makes it slower, but we really don't know exactly the connection. Yeah. Good point. Yes, the monsoon season is in the summer in India or Southeast Asia.
So in the previous study, I was wondering, were you able to define the depth in the end of the detachment, or was it constrained by other geophysical data sets?
The depth was constrained by geologic mapping. So if I show you,
So the detachment was not part of the.
no, we did not. We assume that is a known parameter because based on those geologic mapping.
Oh, okay, from mapping.
Yeah.
All right. Well, if there is no more question, Mong-Han will be here this afternoon. Let's thank him again.
Thank you.